Yeah,
Thank you.
And the floor is yours.
Cheers. So it's the last one for a while. I hope it leaves a good taste in your mouth. So I'll try my best. So yeah, so today, first, yeah, I'm Daniel. I'm from Australia, Monash University in Australia. And I'm going to give a talk here today, which is a modified remixed version of a talk that was given at the Europe's last year by my colleague, Christoph Bergmeier, who is, works in forecasting a lot. And basically, we're going to be the talk is going to be looking at some possible fundamental limitations regarding the use of foundational models in forecasting, which has become a topic of some interest recently. So, what we're going to do is we're going to start off briefly looking at forecasting and foundational models in the forecasting space. Then we're going to talk about something I think is very relevant to foundational models, which is Stein's paradox. And then we're going to finish up very briefly looking at foundational models and context. So obviously it's only 30-something minutes, so the bits have been trimmed here and there. I'll try to keep it not too technical or anything. And as I say, a lot of these are opinions, some are ideas, some, it's not all, I'm not claiming to know everything about foundational models and forecasting, but hopefully some of it is at least thought-provoking. Just very briefly about Monash, where I come from. So Monash University is in Australia, in Melbourne, so down the bottom, and just above the little island of Tasmania. That's where we are on the mainland. And I'm from the Department of Data Science and AI. And we have in the department, we have interests in time series, so forecasting, classification, Bayesian machine learning, deep learning, and a lot of vision, language, and bioinformatics. And our most famous staff member is probably Professor Chris Wallace, who invented minimum message length and was a pioneer and contributor to information theory in statistics and machine learning. And just as a little side note, the department is always looking for collaborations. We have a webpage, obviously, and there's lots of people. There's probably 70 or so staff, including research fellows and tenured staff. And we are able to host visitors, so just a thing. And I guess while I'm at it, I'll do a little advertising for our group. The paper was just accepted, so we have this new repository for time series classification that is built around very large series instead of the small series that were used in the sort of standard benchmark for time series classification. So this was just accepted at the JMLR dataset strand, the new journal they built. So tiny bit of advertising, why not? So let's get started, I guess, on the main content. So what we're going to be looking at is, forecasters. And in our context, or the context of today, we're going to say that a forecaster is some black box that takes an input series and produces some estimate of the future values of that series. So it tries to complete the series for, say, H steps. All right, so we're going to be more interested in short-term forecasting rather than long-term. I don't really have time to discuss why our focus is more on short-term. That's in the fuller version of the talk. But so we're going to we're thinking about forecasting over maybe the next 6 or 10 or 12 forecast units. And the aim in general with forecasting, obviously, is to build some system that produces forecasts that are close, in some sense, to future realizations of the process. All right. So, maybe we have shoe sales for the last 12 months, and we want to forecast how many shoes are going to be sold of a particular variety in the next 2 months, right? So we can do some inventory optimization or whatever. Now, to keep things simple for the talk, we're going to obviously acknowledge that there's lots of other modes of operation. You can have exogenous predictors and so on, but we're going to stick with endogenous type forecasters that use the series and try and complete them. And this is still an extremely common scenario, right? We often don't have a huge amount of side information of that type. So local and global models are the two sort of modes in which you can operate when forecasting. So local models is the more traditional idea, you know, where you have an ARIMA or an ETS or some model. It doesn't have to be one of those, but they're standard examples. And you treat the time series that you get as a data set and you build some model. Maybe you fit an ARIMA model to it, or you learn the parameters of an ETS, and then you forecast based on that series. So that's called local modeling. So each series gets a model. And about 5 years ago, Rob Heinemann and some of his collaborators at Monash introduced this idea of global modeling. So the idea is now that we treat a whole set of time series as data set and we build a model across the series, the idea being that we can now have enough data perhaps to make high variance models more competitive. So in the traditional space where you have a single series and try and forecast, things like deep learning, for example, didn't show particularly great, at least the implementations in the past, great performance because you didn't have a huge amount of data necessarily, right? If you have a yearly series, there's only so many years that can have occurred since 1980. Well, it's difficult to add years, so you're sort of stuck with as many as you have. But now if you find a collection of time series and build a model across them, well, you could maybe say, well, you're going to leverage the fact that you have lots and lots of series, and maybe you can extract some more information from this and use a higher variance model with some success. And more recently, people, of course, start talking about foundation models or foundational models. I'm not really sure what the definition of a foundational model is, but the term is certainly used. Maybe there is a formal definition, I'm not sure. But from from our context, you can think that a foundational model really is just a type of very high complexity global model. So it's a global model learned over multiple series and usually some sort of deep neural net. And specifically, it's usually trained on what you might say is a diverse set of time series. Well, the idea is that you build some model that somehow is good for everything. And you can forecast with it, you can do, doesn't matter what the input series are, you're going to do well. That's the idea, right, behind these foundational models. Now, before even this foundational model stuff started to be a thing, global models were shown to have quite a high degree of success, right? So this paper here from Heinemann and Montero Manso, they introduced and studied these global models. And originally the idea was that the series would have to be somehow related for you to make a huge amount of performance improvements from them. But well, as it turns out that in some sense, you don't really need them to be related per se to have improved aggregate performance. And that's the key thing. So you have a large number of series, you train your model, and then you evaluate on a large number of diverse series, and you find, well, okay, it actually performs quite well on aggregate. But I think that's the very key thing that, this is one of the key things we're going to discuss here, is this concept of aggregating over errors naturally leads us to make this conclusion when the conclusion may not necessarily be valid for what we actually want to do. All right, so we always think about a paper, you get the paper and they show we tested on these 50,000 different problems and we averaged the error and we did really well compared to some other method. And this is implicitly thought perhaps to be a good result, right? You say, well, this is obviously a better method. Method A is now better than method B because its aggregate performance is better. So it does better on a wider range of problems. But it turns out ideas like this have been present in statistical theory for a long, long time, right? Specifically since the 50s. So I'm not sure, does anyone here know what the Stein's paradox is? So well, you'll see. But these two papers that introduced this concept, I think, are two of the most important papers in statistical history. And while I wouldn't say they are underappreciated, as they have thousands and thousands of citations, I think they still remain, in the modern context, underappreciated in how groundbreaking the ideas were. So what we're going to do is we're going to look at a really simple forecasting problem, and we're going to examine this Stein's paradox and then connect it back to foundational models. That's the aim of the talk. So what we're going to do is we're going to create a really simple forecasting problem. The problem doesn't have to be this simple for the ideas to apply. In fact, the ideas are very general, but we want to keep things as simple as possible so we can kind of get a little bit of maybe a handle on what's going on.
So here's a really simple forecasting problem. We observe a single observation, say y, from some Gaussian process, and we're asked to forecast the next value in the series. So we have one observation. And obviously there's not so much we can do when we have a single observation, but we can assume perhaps that it's a stationary process so that the future will be equal to some unconditional mean plus some random deviation. And we can try and forecast, we can build some, using the one observation we've had, we can try and build some forecast for the next point. Right? And if we do that, let's call our forecast, say, y hat f. We can evaluate its quality using the risk, right? It's squared error risk. So we can say what would be the average squared error if I observed y, so if I observed y, built a forecast value, say yf hat, and compared against the actual realization. And maybe we average over an infinite number of realizations. We get our average squared error or our forecast risk. So here's our forecast risk. It's the average squared error of our forecast against the next value. And with a little bit of algebra and exploiting the fact that we have a very simple model in this case, we see that the error reduces down to two components, an irreducible component here, sigma squared, and a term that depends on how close our forecast is to the unconditional mean. So the second term doesn't depend on the forecast, it's irreducible, so the problem reduces here to forecasting the unconditional mean of our process. Now, the forecast error there would be minimized if we somehow knew the unconditional mean. So if we had access to an oracle, we could plug that in, we would get zero error in the reducible component. But obviously we don't, so we would have to estimate it somehow. And maybe we choose to use a standard estimation technique like least squares or maximum likelihood. So we find the mean that minimizes the squared error on the one observation that we have, which would obviously be the value of the observation itself, and we use that as our forecast. So we take our observation y and we say the next value is going to be equal to y. And in this case, the squared error for the reducible component here would be given by mu minus mu hat least squares, which is just y, and y here has this form. It's mu plus some zero mean Gaussian noise. So we can plug this in, cancel our mu's, and we see the squared error is sigma squared. And this forecast is actually optimal in some sense. So what we can say about this is if the underlying process, it doesn't even have to be Gaussian, by the way, but let's say it's Gaussian. The underlying process is this stationary Gaussian process, then, and we observe y, then using y to estimate the mean will be optimal in the sense that it's the uniquely minimax and admissible estimate. So what do I mean by that? I mean that minimax means that it minimizes the worst case squared error. So across all possible mu's, you have, in this case, constant risk. It doesn't matter what mu is, the risk is constant. And it's admissible in the sense that there's no other rule you could derive from this single observation that would uniformly outperform the least squares estimate. Right, so in this one-dimensional problem, the least squares estimate is optimal under these conditions. Cool. So let's generalize the problem a little. And instead of seeing a single observation, we now have, say, p observations from p different Gaussian processes, each with different unconditional means. So instead of having one observation, we have 10 or 20 or 30. Right? We have one observation from each of these different processes. Now the processes are independent, so they're statistically independent. And now the problem is we want to forecast the vector of means, right? Rather than a single mean, we want to forecast the vector of means. And we can assess the performance of any forecaster that we come up with in a similar fashion as before. We take our initial p-values, one from each process, and we form some forecast based on them. And we see that with a little bit of algebra, that reduces to trying to estimate this mean vector with small squared error risk. So again, we have this irreducible component, p times sigma squared, because we now have p different processes, and we have this reducible component here. So this is called something, this is something in statistics that's known as the multiple means problem, because not the most creatively named problem, right? But we have multiple means and we want to estimate the mean vector, right, as a whole. Now you might think, oh, all seems a bit abstract and such a simple model, etc., etc. But we think about it, such problems are actually pretty common for starters, right? So imagine that we're forecasting the primary votes of a bunch of parties in an election based on a survey that we did last week, right? The exact problem here is to try and estimate the means as accurately as possible of the single observation that we've taken. And when I say a single observation, I would say, for example, in the case of that, you might observe some single realization from some binomial random variable, which is the number of people that voted for the different parties. And there's lots of different problems that can be recast into this simple framework. And in fact, it turns out that if your model is sufficiently regular, then for large samples, maximum likelihood or statistical estimation reduces to a form of multiple means in the limit. So the multiple means can even be thought of as being maybe the only problem that exists asymptotically. But that's a little bit of a sideshow. So here we're thinking about observations and we want to forecast the next ones. So we need to estimate this mean vector, and we'd like to do it in a fashion that has small squared error risk, right? Small average squared error. So what we could do is we could again use least squares, right? We could say, well, if least squares is optimal for each coordinate, I can just apply least squares to each coordinate separately. They're independent problems, and I should get a good solution. So this is a type of local forecasting model, right? We're learning a model for each of the series independent of the others and making a forecast. And if we do that, by the separability of the problem, it's pretty easy to see that the expected squared error of this estimate, so mu is the true mean vector and mu least squares is the least squares estimate, so we just take the vector of observations and use them as our estimate of our mean, this has a risk of p times sigma squared. So that's the baseline risk that our least squares method has. And now the problems, as I said, are independent, and the least squares rule is optimal for each coordinate, so we would conclude that this is the optimal solution, right? Yeah, I guess. Would you, if I didn't have ask a leading question, would you probably say that yes, this is going to be the best way that you can estimate this vector of means from this single vector of observations? And most of us, I'm sure, would have said yes, if you haven't seen the literature. And most statisticians said yes until 1956. So the answer to the question of whether this is an optimal rule for estimating mu, and therefore in this case making our forecast, is that it's not necessarily an optimal rule. Specifically, Charles-Stein in 1956, and then James-Stein, so James was his PhD student who I think contributed exactly one paper to statistics before deciding it wasn't for him, and it was this groundbreaking paper. They proved the following interesting facts. So they showed that the least squares estimator, regardless of the dimensionality p, is a minimax rule. So it minimizes the worst case risk against mu. So it doesn't matter what the configuration of mu is, your worst case risk is always as small as it could be. And they showed that if the number of dimensions of this vector is less than 3, then least squares is admissible. So there's no other rule that you could come up with that would uniformly dominate least squares. So in dimensions 1 and 2, we can say the least squares is the way to go, right? But then they showed that if the dimensionality is 3 or greater, the rule is actually not admissible, which means that there exists ways of estimating mu that have strictly lower squared error risk for all configurations of mu. We say that an estimator dominates another one if its risk is nowhere worse and somewhere better, right? Now that was the 56 paper, and then in 61 they showed that, James and Stein introduced an estimator. They constructed one that actually dominates least squares. And it's called, unsurprisingly, the James-Stein estimator. Very creative naming back in the day. Perhaps that's not necessarily a bad thing. Maybe some of the names these days are so creative you don't really know what they're doing. But James and Stein proposed that instead of using the vector of observations as an estimate of mu, you should take the vector of observations and multiply them by some factor c, which is generally less than 1. Sorry, it's less than 1, but it's generally between 0 and 1, which we call a shrinkage factor. So we take our whole vector of y's, we sum them up, or square them and sum them up, and we take p on 2 on top and divide and then subtract that from 1, and we get our shrinkage factor. And this is a type of global model, right? Because now we're learning, part of our forecast is learned across the series. Right? Before we just used observation y1 to forecast mean 1, y2, mean 2, and so on. But here we are using not just observation y1 to forecast y1, but all the observations, because they are forming the shrinkage factor. So this is a type of global model, a very simple global model in some ways, and perhaps, you know, one of the only, well, it's not the only, but it's a simple global model, but a very important one. And as I said, the consequences here extend trivially beyond this simple problem. And they showed that if p is greater than or equal to 3, this rule here for estimating mu will have strictly smaller average squared error at estimating mu than the least squares estimate, which has a risk of p times sigma squared. So it doesn't matter that I mean, you're probably thinking, well, they're independent. How is this possible, right? How could you leverage information from one coordinate to another if they're statistically independent? And, you know, if you read the literature all the way back then, which I enjoy to do, I like the history of statistics, you'll see that a lot of people, there was a controversy when this idea was introduced, right? It was, people were asking, well, how is this possible? Is this some mathematical trick? Is it nonsense, etc., etc.? Which is a reasonable question to ask. Because what the James-Stein estimator does, it seems to do the impossible, right? It combines potentially unrelated problems together and somehow improves the estimate on all of them. Now, so how is that possible? So one of the questions, or this is a paraphrasing of a question that, you know, was facetiously asked, is that, well, so if I want to estimate the tea consumption in Japan, I would somehow do better if I simultaneously estimated also the speed of light and the weight of hogs in Montana. Right? So you can see Efron, it's 1973. He asked this question somewhat facetiously and then proceeded to answer the question. And it's a reasonable one, right? If we somehow get a smaller average error on mu, then it suggests that enlarging our problem could somehow lead to improvements, even if the problems are unrelated. So there's two ways how this paradox, that's why it's called the Stein's paradox. So there's two ways of answering the paradox. The first is to note that just because you say things are unrelated doesn't mean they are. So in the case of the Stein estimator, if all the means of the vector happen to be close to 0, and we shrink towards the 0 vector, then ipso facto they must be related simply by having a similar magnitude. Right? So the first thing to take away is that just because you say things are unrelated doesn't mean they are. But the second is, if we look at the properties of the risk function itself, we see that while the aggregate squared error at estimating mu under the James-Stein estimator is strictly lower than for the least squares estimator, the maximum possible risk for the worst case coordinates is of order square root of p times sigma squared. So what does that mean? It means that if we aggregate across the risk, the aggregate will in general be small, well, on average be smaller, but the worst case performance for any single dimension can be substantially larger than the least squares estimate, which has a fixed risk of sigma squared for each coordinate. So the shrinkage can improve the overall estimate at the expense of damaging the estimates for one or two coordinates if they happen to lie far away from the rest of the means in this particular simple case. So what we can say is that the James-Stein estimator improves estimation of the whole object mu at the expense of specific elements of mu. So that answers our question above. Yes, I do want to estimate tea consumption in Japan and hogs, the amount of hogs in Montana, and the speed of light simultaneously if I judge that the average error of these three is somehow a quantity that is valuable or useful to me. And if it's not, well, perhaps we shouldn't be doing that. So yes, we do want to estimate things simultaneously, but only if simultaneous estimation or having small simultaneous estimation error is relevant. Now, just on a side note, I'll also point out that these ideas somewhat occurred similar time with, of course, now as soon as I go on a tangent, I forget the name of the, Robbins, one of the key people behind exploitation, exploration and bandits and so on. He also had a series of papers on what they call compound decisions, so making simultaneous decisions. So there's a whole rich amount of literature in the 50s and 60s that I believe personally is somewhat untapped and underappreciated in the modern era. So you might ask yourself then, okay, obviously it's probably nonsensical to simultaneously estimate these three things with better risk, because why would we be interested in these three things simultaneously as a whole? So are there any problems where it makes sense to estimate the whole of mu rather than some individual coordinate? I guess I ask if anyone has any ideas off the top of their head, a problem that where this might actually be useful. Well, it turns out that it's very useful in a very common model that all of us, I'm sure, have used at one point or another, and that's linear regression. So sometimes estimating the whole object well is more important than any component. So if we think about a linear regression model, we say that our y is a linear combination of our weights and our predictors, and our interest is in the overall combination. If we're interested in prediction, we want to predict the overall combination well. We're not necessarily interested in estimating any of the single coefficients well. Now, we may be, of course, if what we're interested in is finding the coefficient relating some drug to the amount of malaria, deaths, or whatever, then that's the thing we're interested in. But if we're interested in predicting, we don't really care if we get a particular coordinate slightly worse than we would under least squares if all the coordinates on average are estimated better, because our prediction is the overall combination. So if we apply, for example, James-Stein estimation to linear regression, which was done, as you could probably imagine, very quickly, right? One of those low-hanging fruits, even lower back in the day in the 60s when there were so few people working. Very quickly, a paper came out showing that it's trivial to adapt the same rule, more or less, to linear regression, and you end up with an estimate of the coefficients that strictly dominates least squares estimates of the coefficients in terms of prediction risk. And if you stop and think about it, you start to realize that why this paper is so important is because it forms one of the theoretical foundations for the entire field of regularization. So in regularization, we are interested in reducing the overall variance, say, at the expense of a little bit of bias, so we accept damage in some of the coefficients if we can improve the overall prediction error of our process. So people have moved away to some degree from things like maximum likelihood purely, even though they give you maybe some nice guarantees of unbiasedness, because we're more interested maybe in prediction. We have a large number of predictors, so we're happy to sacrifice the performance on one or two coefficients if we get an overall better prediction error. And it's not just James-Stein, the same applies to all the regularization techniques like Lasso, or all the Bayesian approaches have this similar flavor, right? Probably just never, can't say that you did or didn't, but maybe you didn't think about it that way, that's what you're doing. You are not going to be able to improve uniformly across all the coefficients. but you don't need to. So what you'll find is you apply something like lasso, is that in worst case, you could actually have quite a poor error on some of these coefficients, right? If you apply L1 regularization, maybe you shrink a bunch to zero that were actually relevant and you've incurred a fair bit of perhaps error on those coefficients. But if they only constitute 3 or 4 or 5 out of a 10,000 or 100,000 things that you're estimating, then the aggregate error will be reduced. So sometimes that's exactly what we want to do. We want to reduce the aggregate error. But sometimes I don't think it is something that we want to do, right? So if you think about aggregate risk reduction, it's a very egalitarian thing to do. The individual's interests are subordinated to the interests of the group, right? We say, well, you might have a worse outcome, but the group does better, so we judge this as a success. But maybe that's good as writers of papers and creators of new methods who need to get a certain score below a certain threshold to get into NeurIPS or something, right? You know, we've got maybe a Kaggle competition or whatever it is, right? We have this idea that we are sort of having to beat the latest score, so we look at our aggregate error. That's important. But in practice, if you think about it, a forecaster is not interested in your aggregate error over a bunch of random data sets, no matter how diverse they are said to be. They're not interested in your aggregate error over this set of data sets. They're interested in how well it performs on their particular problem, right? So there's this, I guess you could say, a bit of selfishness, right? It's like, well, I'm not concerned that you did well on these 50,000 problems. If my problem happens to be one of the ones where the risk is very large, I don't like this. So in general, you might say that these type of foundational global models that are trained on large diverse sets and then evaluated on similar sets, they are, I mean, it's not that they're not doing what they say they're doing. I'm not trying to say that, but I guess I'm asking you to think about whether that's actually a good thing to judge the quality of something on, right? So it's obviously great for the paper if the paper does well on average across a diverse set, but in practice, like I said, I'm interested in a specific problem. And so if I take a foundational data set and train it on a whole bunch of data from different dynamic processes that are, very high signal to noise ratio and lots of data, and I get great aggregate performance over all these, robot arm and all the basic sets. And then you say, this is my foundational model, and it gets a really good average aggregate score. And you hand it to someone who's forecasting the GDP of some country off 12 observations. And there's no guarantees that the average error that you get with respect to this diverse set is going to in any way replicate in this new specific problem. Well, there's no guarantees, but the guarantees are much weaker, right? We see that there are, in fact, some form of guarantees in this, even this simple problem. We know that the worst case risk is of order square root of p times sigma squared. But I mean, you don't know that your problem is a good one or a bad one for the particular foundational model. So perhaps evaluating models in this fashion and having maybe a leaderboard that you are trying to beat for publication is maybe not. This is my controversial take that, that maybe research by Kaggle competitions isn't the way to go, right? So anyway, that's my only controversial statement. But I think that personally, this approach is not necessarily the way to go when you are building these types of foundational problems, because in some way you're setting up a problem to win, not a problem that you create, but I'm not sure if it's necessarily a problem that actually applies in real. Anyway, I'm happy for people to push back or whatever later on. I don't mind. I'm just checking that out. So we're going to finish off by just bringing it back here to foundational models. I do want to add a stress again that while the Stein's paradox seems simple on the surface, the model, it applies very generally across any problem of simultaneous estimation. Right? So even the specific formulae that people derive for the Gaussian case trivially holds for, or with minor modifications for non-Gaussian and so on. Right? It's not tied to some trick of the simple specification of the model. It's about simultaneous estimation. So if we go back to foundational models, because we're in the era of deep learning, I guess the answer to solving the problems, right, is pretty clear. We just collect an even more diverse body of data. Our body of data was not diverse enough, so we now, instead of having 10 million data sets, we collect 100 million, and now we're going to solve the problem, right? The problem will disappear. And I'd say that yes, this might actually work. It's probably very likely to work if the problems you're looking at, you know, are long, you have long time series with high signal to noise ratios, so that the contextual clues about the future realizations are very clear in the series. Right? If I have some, you know, nonlinear armor model and I sample it for 100 million steps, of course I'm going to probably be able to predict very well the next 10 realizations from this nonlinear armor model. But of course, in practice, there are actually a lot of applications that don't meet this particular condition, right? Long series, high signal to noise ratio. That seems like a very pleasant regime to be operating in. But low granularity series are, of course, extremely common. And lots of companies and industry, governments, they're interested in forecasting specifically low granularity time series. So let's have a think about, you know, most supply chains that you might work with, they run on monthly planning cycles. So you're going to get monthly data. Yep, almost finished. Yep, monthly data. Most macroeconomic series have slow dynamics, right? So you might say, well, okay, you have 100 days of data, but I could sample every 5 minutes and I could make, you know, 50,000 times that amount of data. Now I have all the data I need. But I mean, you have to think about, it's like, for example, would you say, let's forecast the 5-minutely unemployment rate, right? It's nonsensical. I'm not going to be forecasting the unemployment rate in the next 5 minutes. So the dynamics of a lot of these processes are slow. And as an example, we have here this Federal Reserve Economic Database from the US. Majority of the series here that are economic indicators are annual. And there's only so many years we can have in the last 30 years, right? About 30. So a lot of series are short and noisy. So what can happen is, you know, we get a very diverse set of data sets to train on. So maybe we start off with this training data here for our foundational model. We have a whole bunch of these from some source, and we train our model and we forecast and we see, it does really well. But then we say, well, we want to be more diverse, so we add in a bigger, wider range of series. We add in maybe some GDPs. And we train across both of them and build our foundational model, and we have more data, so it's obviously going to be a better model. But of course, what happens is that in this case, especially with low granularity series, is that the context of the series itself isn't a particularly good indicator of what's going to happen next. And these are both real series. This is series that are, I believe, power output of a solar cell or some solar panel, so it goes up and it goes down. And over here, I think, are taken from some GDPs. So what happens, of course, is that foundational style models that just use this training data, they're going to do some sort of implicit model averaging over all the submodels implicit in your large deep neural net, specifically to minimize aggregate error. So in this case, you're going to minimize aggregate error across these series by going somewhere in between them. Whereas if we think about perhaps a simpler, maybe a local linear trend, well, for the first class of models, it's going to perform quite poorly, but for the second, it's going to perform very well. So now you're sort of left with the question, right? From a point of view of a publication, the smaller aggregate error is better because you've got a smaller aggregate error than, say, using a linear forecaster. But would anyone ever want to use such a model, right? Because it doesn't do well for any of the series that perhaps people happen to be interested in. So when the linear trend is used appropriately, it, of course, is much better. So to finish off, my last main slide is that to address this, I think the key thing is that we need to start thinking about adding context into foundational models, so multimodality, if we want them to do better. So if we can tell the model that this is a GDP and this is a shoe sales and this is whatever it happens to be, then you can start to add extra contextual information that will allow the model to implicitly select a better forecast based on this extra information. So I think that not only is it not just something nice to have for better accuracy, but I believe that it's going to be the fundamental way to get foundational models that are truly foundational over a wide range of problems, not just ones that have high signal to noise ratio and very large numbers of data points in their series. Something that performs better overall in actuality, whose worst case performance is reduced, not something that just performs better at the expense of something else. So here's an example from a paper. Other people are working on similar ideas, but we see there's a time series very similar to the ones I showed before. I mean, the ones before were kind of cartoon representations, but here is the power output of a solar cell over the previous 90 days, daily, or, I think it's every hour. And you can see that, you feed it into some standard foundational model, and it, of course, what's it going to do? It extends, right? And on the right is a context-aware forecast where it has an idea of what this time series is. So, in conclusion, I guess what I want to say is that it's always possible to improve the aggregate error at the expense of the individual error. And as such, it sort of depends on the training set that you build your foundational model on, whether it's going to give good results for your use case. And just adding more and more data isn't necessarily going to make your model better, because there's still limits on how well it can identify what it needs to do endogenously only. So the inclusion of context here, we believe, promises the way forwards to build even better foundational type models. And so I just want to say that this is a cut down / remixed version of a longer talk given by Christoph Bergmeier at this NeurIPS workshop last year. And the slides are here. I encourage, if you thought this was of some interest, to watch this talk, because it has another whole section about practical evaluation in papers and some interesting results that have occurred perhaps through to, I don't want to say, anyway, it's about perhaps some papers' testing regimes are not as rigorous as they should be. Let's say that. I think that's a nice way of putting it. And there's a whole bunch of extra material on that. So I encourage, if you're interested in forecasting and time series, to have a look at this talk as well. So thank you for giving me your attention. I know that it's these days, people don't often come to talks. So thank you for giving me half an hour of your time. And if you have any questions, fire away.